How do we print tens of billions of tiny details onto an area no larger than a human fingernail? This is not just engineering anymore. It is a profound challenge to the fundamental laws of physics. Welcome to the world of EUV, where humanity creates a light that does not exist. To understand this, imagine a single transistor. It is tens of thousands of times smaller than a human hair, yet we must place billions of them. Standing in the darkness of the world's most advanced cleanrooms is a machine that dominates the future of every single chip on our modern planet. This machine generates extreme ultraviolet light, a radiation so rare it is naturally absorbed by Earth's atmosphere, making it nearly impossible to harness or control. By mastering this light, humans have unlocked the ability to etch the smallest patterns ever made, securing our dominance over the next generation of technology. This is the story of the most complex machine ever built by man, a $200 million marvel that makes the modern digital world possible. Extreme ultraviolet light is the key. Without it, the progress of our civilization's computing power would have hit a dead end many years ago. For decades, Moore's law held true as transistors shrank. But eventually, we reached a physical wall where traditional light was simply too thick to draw. The old technology, called DUV, used a wavelength of 193 nanometers. It was like trying to draw fine art with a giant marker. When transistors dropped below 7 nanometers, the 193 nanometer light became too blurry. We needed a sharper tool, something much smaller and far more powerful. Enter EUV. With a wavelength of only 13.5 nanometers, this light is sharp enough to carve the features of the world's most advanced chips. However, EUV light has a massive catch. It is so energetic that it is absorbed by everything, including the very air that we breathe right now. Traditional glass lenses are useless here because they absorb the light instantly. This forced ASML to reinvent the entire concept of how a camera works. To use this light, we had to move into the vacuum of space, metaphorically speaking, creating a machine that operates in a perfect, airless void. The stakes are astronomical. Every nanometer we shave off allows for more speed and less power consumption, driving the entire global economy toward the future. We are operating at the very edge of what is physically possible. One step further, and we are fighting the basic nature of atoms and light. This is why the EUV machine is so vital. It is the only way to continue the digital revolution that has defined the last 50 years. Transporting this machine is a feat in itself. It requires 3 massive Boeing 747 cargo planes just to move the components of a single EUV system. With over 40 shipping containers and a dedicated team of 20 specialized engineers, the assembly process of one machine takes months of precision work. Inside, you will find over 100,000 individual parts, linked by 2 kilometers of complex cabling and hundreds of high-pressure fluid systems. The cost of this single machine is a staggering $200 million. It is likely the most expensive piece of equipment in human history. Weighing 180 tons, this giant is as heavy as a fully loaded airliner, yet it moves with the precision of a surgeon. At its core is a vacuum chamber, where air molecules are pumped out to a level cleaner than the void found in outer space itself. The optics, crafted by Zeiss in Germany, are the most precise mirrors ever manufactured, designed to guide light with zero margin for any error. Every single one of the 100,000 parts must work in perfect harmony. If a single sensor fails, the entire multi-million-dollar process halts. The machine is so sensitive that it can detect the vibration of a footstep from across the building, requiring advanced magnetic levitation to stay still. It is a monument to human ingenuity, a physical manifestation of our desire to conquer the microscopic world through sheer engineering will and determination. Now, let us look at the heart of the monster. To create EUV light, the machine must perform a terrifyingly violent and precise dance. A generator spits out 50,000 droplets of molten tin every second. As they fall, a high-power CO2 laser strikes each one with perfect timing. The first laser pulse flattens the droplet into a disk. A second, much more powerful pulse then vaporizes it into a brilliant, glowing cloud of plasma. This plasma reaches temperatures of 220,000 degrees Celsius. That is 40 times hotter than the surface of the sun itself. This process repeats 50,000 times every single second. It is a continuous explosion, managed with a precision measured in billionths of a second. The result of this violent interaction is the precious extreme ultraviolet light, which is then captured and focused by a specialized collector mirror assembly. If the laser is off by even a fraction of a millimeter, or a nanosecond of time, the light disappears and the chip is ruined. The engineering required to move molten metal at 70 meters per second and hit it twice with a laser is simply mind-boggling to conceive. Debris from the explosions must be cleared instantly. A constant stream of hydrogen gas protects the optics from being coated in tin vapor and dust. The laser system alone occupies a separate floor, generating enough power to cut through steel. Yet here it is used to tap tiny droplets. This is the source of the light. But creating it is only half the battle. Now, we must guide it with absolute, impossible perfection. Since no glass can reflect EUV, ASML uses mirrors. But these are not ordinary mirrors. They are composed of hundreds of alternating atomic layers. These mirrors are the flattest surfaces ever made. If scaled to the size of Germany, the largest bump would be less than a single millimeter high. The light reflects off 6 of these hyper-flat mirrors. Each reflection loses some energy, so the initial beam must be incredibly powerful to survive. To achieve this, Zeiss engineers must deposit layers of molybdenum and silicon with atomic-level precision, a process that takes months for a single mirror. The mirrors are controlled by actuators that can adjust their position by the width of a single atom, fighting against gravity and heat expansion. This entire optical path must exist in a perfect vacuum. A single molecule of air in the wrong place could block the light entirely. The environment is cleaner than any hospital operating room. A single speck of dust inside the machine would be like a boulder hitting a car. The silicon wafer itself is held on a stage that accelerates faster than a Formula One car, moving into position for the light to strike. The EUV light passes through a mask, carrying the architectural design of the chip, and is projected onto the wafer with 4-fold reduction in size. This is the pinnacle of human precision. We have reached a point where we are using light to build machines at the scale of molecules. ASML does not do this alone. It is the hub of a global network, relying on thousands of suppliers from Germany, the US, and beyond. Because of the sheer complexity, ASML is the only company on Earth capable of making these machines. They have a total 100% monopoly.
We are prepared to increase our bid by 20%.
Companies like TSMC, Samsung, and Intel are in a desperate race to buy every machine ASML can produce, with wait lists spanning several years. Without these machines, there would be no 5nm or 3nm chips. Your modern smartphone, your AI, and your cloud servers would simply stop evolving. This has made ASML a central figure in global geopolitics. These machines are seen as the crown jewels of Western technology and national security. The export of EUV technology is strictly controlled. Owning these machines means owning the future of artificial intelligence and military superiority in the digital age. It is more than just an industrial tool. It is a strategic asset. A single EUV machine can shift the economic balance of power between nations. The dependency on this one company is a bottleneck for the entire human race, making ASML perhaps the most important company you have never seen. Every time a new iPhone or a more powerful AI model is released, it is a victory for the engineers in Veldhoven and their incredible machine. The scale of investment is billions of dollars, and the payoff is the ability to compute faster than anyone else on the face of the Earth. But the race does not end here. ASML is already building the next generation, called high-NA EUV, to push transistors down to the 2nm level. We are reaching the point where we can etch patterns that are as small as the molecules that make up the very building blocks of life. From the explosion of molten tin to the hyper-flat mirrors, every part of this journey was once considered impossible by the world's greatest scientists. The chips made by these machines will power the next generation of human discovery, from curing diseases to exploring the furthest reaches of our galaxy. It is a testament to what we can achieve when thousands of the brightest minds collaborate to solve a problem that seemed fundamentally unsolvable. When you hold your smartphone today, remember that inside it is the result of a plasma hotter than the sun and mirrors flatter than a horizon. The EUV machine is the heartbeat of our modern era, the silent engine driving us toward a future where computing power has no known limits. ASML and the EUV process have turned the impossible into the everyday, etching the destiny of our digital civilization 1nm at a time. Thank you for watching the journey of the machine that rules the world of chips. The future is bright, etched in the light of EUV.